Hello guys, welcome to the 13th class of this course. In the last class, we talked about the calculus of variations. So there we learned that if, so let's say point 1 from point 2, the particle goes from point 1 to point 2, then the path is given by y. So in that case, we can define a function f which will be uh, a function of, so f is a function which we will call the Lagrangian. So later we will call it a Lagrangian. So it's a function of y t alpha. Alpha is the parameter that varies the path. So if alpha is different, if alpha is something else, so the path will be it will be a different path. So it's so this f is a function of this y dot and time. So if the particle moves in time, okay. So in that case, we can define a quantity called action, which is from t1 to t2, line integral of this f along this path. So f of y t comma alpha y dot t comma alpha comma t dt. So from Hamilton's principle, so we use the Hamilton's principle, and the Hamilton's principle said that if we are at the, or if the actual path is given by yt0, then the variation of this action at the point where the path is actual path, it will be 0. Okay, so that's the principle. So this is called the Hamilton's principle. This is called the Hamilton's principle. So from this Hamilton's principle, we derived that for the actual path, when this delta j is 0, this function will follow an equation which is like ddt of delta f delta y dot minus delta f delta y equals to 0. So this was the discussion of the last class. So here we will use this equation, so this action principle, to solve a few simple problems. So problem 1. The shortest distance or the shortest path the shortest path between two points. Let's say x1, y1 and x2, y2 in a plane. So obviously we are using the Cartesian coordinate here. So if we have a plane with coordinate system as the Cartesian coordinate x and y, and let's say these are the 2 points. These are the 2 points. This is x1, y1, and this point is x2, y2. So then we will find out what will be the shortest path between these 2 points. So we already know the answer. That will be a straight line. So let's see how this Hamilton's principle, so its calculus of variations, uh, gives the answer. Okay, so we will use the calculus of variations to derive that the shortest distance will be a straight line. So the distance is defined by ds, the infinitesimal distance between two very very little separated points. So it is given by, so ds square is given by dx square plus dy square. That means the distance between two neighboring points, so infinitesimally close points, is given by root under dx square plus dy square. So which is basically root under 1 plus dy dx. If we take the dx outside, then we will get dy dx whole square times dx. Now we will write this dy dx as y dot. So it's not a derivative with respect to time, because here time is not in the picture. So here the independent variable you can treat it, you can consider kind of this x. So here x is analogous to the t in this equation. So here the part of t is played by this x. So then if we go along from this point 1 to point 2, then the total distance, that will be s, will be given by integration ds from point 1 to point 2, which will be from x1 to x2, 1 plus y dot square dx. So now we want, so this is the action. So this is called the action now, which is basically the distance between, or let's say not distance, let's say the path traveled between 1 to 2. We will use this Hamilton's principle, and we will state that if this action S is stationary or extremum extremum, then delta S equals to 0. In that case, this term, so this term is analogous to this Lagrangian, this f function. Okay. So in that case, this term will follow the equation. So we'll define it by f. This term will follow this equation in that case. So in that case, we will say that ddt of del f del y dot minus del f del y equals to 0, where f is root under 1 plus y dot square, right? So now if we do this derivative, then it will be ddt of what is del f del y dot. It will be half root under 1 plus y dot square into 2y dot minus 0 will be 0. There is no y dependence in f. So del f del y will be 0. Okay, 0. So we will get then ddt of y dot root under 1 plus y dot square equals to constant. Sorry, it will be 0. So if it's 0, so we know that the derivative of constant is 0. So in that case, this term inside the derivative will be a constant. Let's define it by a. In that case, we will get y dot equals to a root under 1 plus y dot square. Implies if we square both sides, we will get y dot square equals to a square plus a square y dot square. Now if we take the y dot this side, then we will get 1 minus a square y dot square equals to a square. In that case, we will get y dot equals to root under a square 1 minus a square. Let's call it m. There will be a plus minus sign because we are taking the root, but we are so we will include this plus minus sign in the m. So m can take positive, negative value depending on what, depending on whether here is plus or minus. Okay. So m is a constant. So this a is a constant. So this whole term will be a constant. So then we will define it by m. So in that case, dy dt equals to m. So this implies dy equal to m dt. So you can write dy equal to m dt. And if we do the integration both sides, so in that case, we will obtain y as a function of t, which will be mt plus integration constant. So now you recognize this equation. This is the equation of a straight line, right? Equation of a straight line as we expected. Sorry, this is not dt actually. There's a big mistake here. So here the independent variable is x, you know, this x. So here t is x. So ddx, y dot means dy dx. It's not dy dt. Okay, it's a serious mistake. So apart from that, it's correct, I think. Yes. So ddx of this term is 0, then this term will be a constant, and here. So here y dot equals to m. So dy means m dx. Okay. Because y dot is dy dx here. So you can see here, this term we defined as y dot. So this is dy dx. So in that case, what we will get is y as a function of x. Okay. So we'll get y as a function of x, y equal to mx plus c. This is the equation of a straight line in plane. Y equal to mx plus c. So let's not write this extra term. It is already implied that y is a function of x. Okay. So the shortest distance between 2 points is a straight line. So the variational principle, it is such a powerful principle. So you will see with this principle, in the next class we will derive that the Lagrangian equation that can also be derived from this principle. And this variational principle, it has use, beyond classical mechanics. So this use of action to form an action and make its variation zero, it has a use also in the field theory. There also we talk about action. So let's do another problem where we use the calculus of variation. Okay, one more thing which I forgot to mention is that if we try to find that what is the shortest distance, what is the shortest distance. So if you have a circle, if we have a circle, not circle, sorry. If we have a sphere, so in that case, it's a sphere, it's a sphere. In that case, there are 2 points. If there are 2 points on that sphere, and we want to find the shortest distance between these 2 points while we will stay on the surface of the sphere. So that we can also derive by this variational principle. So here that path is called the geodesy. Okay. So if we have time, we will do it in the problems. So when we will solve the problems, we will do that problem, like finding the shortest distance between 2 points on a sphere. So here, problem 2 on calculus of variations, which is finding the minimum surface of revolution. So let's state the problem first. This is the z axis, this is the x axis, so this is the y axis. So and there are 2 points in the xy plane. There are 2 points in the xy plane. So now we want to find a curve joining these 2 points such that if we rotate this curve around the y-axis, so if we rotate this curve around the y-axis, sorry, if we rotate this curve around the y-axis, so then it will look like this. So here also it will be a similar way. So in that case, the surface area, so it will be a plane, it will be a a curved plane, curved surface. So the surface area of that surface, that will be maximum. That's our goal. So we want to find a curve. So what we want to find? We want to find the equation of this curve joining these 2 points such that if we rotate the curve around the y-axis, then it covers the surface, and the area of the surface we want to minimize it. Okay. So let's say this point is point 1, it is x1 y1, and define this point as point 2, which is x2 y2. Now what we want to do is, so let's say let's say we have a curve, and so let's say we have a curve. Let's draw it again. Let's say we have a curve, and this is how we want to rotate it along the y-axis. It will be in a similar. So this two will be symmetric. The drawing is not clear actually. I'm not very good at drawing. So x1, y1, x2, y2, and let's say at some point this is the area. Here also there will be a kind of area. So if this distance from the y-axis is x, okay, of this strip, so in that case, the area of this strip will be 2 pi, let's define it by ds, let's define it by dA, because we have already used this ds to define the length, define the distance between 2 points. So here for this curve, the area, let's define it by dA. So it's an, so this strip, it's an infinitesimal, infinitesimal area. So this length, it is infinitesimal. It is defined by ds. So dA equals to 2 pi x, which is the circumference of this, with this of this ring, and times the ds. It's a very small strip kind of thing. So in that case, what is ds? ds is basically the infinitesimal distance, which is defined by root under x dx square plus dy square. So in that case, we will get it as, so if we take the dx outside of the integral, then we will get one plus dy dx whole square dx. So again, let's define this dy dx as y dot. It's not dy dt, it's dy dx. Y dot is here, dy dx. So in that case, so the total area will be, the total area, this dA is called the infinitesimal area of this strip. So in the total area of this, whole surface, if we rotate this this curve along the y axis, so that will be integration of dA from point 1 to point 2. In that case, we will get from x1 to x2, it will be 2 pi x put under 1 plus y dot square dx. So we want to minimize it. So we want to find the extremum value of this a, which is, so we can call this a as the action, and we want to minimize the action. In that case, this function will play as the role of Lagrangian, this f, if you remember this variational principle. This is the action where the quantity of except this dt part, is the Lagrangian. And we want to minimize, or not minimize, we want to extremize this j action. So in that case, we will get the equation which is called the Lagrangian equation. Okay. So this is for one variable. For multivariable, we will derive it later. Here, similarly, this is the action. We want to minimize it. So in that case, this f, it will follow an equation like ddt of del f del y dot. Oh, again, I'm making the same mistake. It's not ddt, it's ddx. X is the independent variable here. Y dot minus del f del y equals to 0. So where f is 2 pi x root under 1 plus y dot square. So in that case, del f del y, it will be 0. So we will have this ddx of del f del y dot, which is 2 pi x, and there will be root under 1 plus y dot square, y dot equals to 0. In that case, this term inside this ddx, it will be a constant, because only the derivative of a constant is 0. In that case, we will get 2 pi x y dot under 1 plus y dot square equals to let's say c dash. Now if we take this 2 pi here, then c dash by 2 pi, which will also be a constant, and let's define it by c. In that case, we will have the equation like x y dot by root under 1 plus y dot square equals to c constant. Then we will get x y dot equals to c root under 1 plus y dot square. Now if we square both sides, then we will get x square y dot square equals to c square plus c square y dot square. So in that case, if we take this term in the left side, we will get y dot square x square minus c square equals to c square. So we will get y dot equals to c root under x square plus minus c square. And this y dot means dy dx. So y dot means dy dx. So in that case, if we solve the equation, so if we put the dx in the right side, it will be c dx root under x square plus minus c square. And if we integrate, then we will get y equal to c cos hyperbolic inverse x by c plus some constant, let's say b. So in that case, x will be c times cos hyperbolic of y minus b by c. So this is the equation of the required path, of the required curve. Equation of the required curve. So if we take a curve like this, which satisfies this equation, so if we draw a curve from this point 1 to point 2, which satisfies that equation, And if we rotate the curve along the y-axis, then the area it will cover, that will be the minimum compared to any other curve you can consider. So this curve, it has a special name. It is called the equation of catenary. Okay, it looks like this. So in the xy plane, it looks like this. Okay. So it's not a parabola. So this point will be B, and corresponding to this point, it will be C. So let's say these are the 2 points, x1, x2, y2, and x1, y1. And now if we rotate this curve along this y-axis, then rotate this curve, then the area it will cover, that will be the minimum. This is how we can apply the calculus of variations to different kind of problems. Now notice one thing. Here we want to find the minimum surface of revolution, the minimum surface. Okay. Here also we want to find the shortest path or the minimum path. But the calculus of variations, the way the Hamilton's principle is defined, so this equation will satisfy if J is extremum. So it's not necessarily be minimum, it can also be maximum. So here what we are showing, actually, we are not showing that this is the straight line is the equation for the equation for the shortest distance between two lines. We are showing that it's the extremum distance between 2 points. To show minimum, we need to do further. We need to take another derivative of this action to really show that it's a minimum value. And then at this point, so where we are getting this extremum, at this point, if we get a negative value, then we can call it's a maximum. If we get a positive value of this second derivative, then we will call it a minimum. So here what we are doing is not necessarily not exactly calculating the shortest distance. We are actually calculating the extremum distance. Okay. So, but the maximum distance will be can be anything. I mean, it can be infinite, because we can go any from. I mean, you can take any round path between these 2 points. So this equation must be giving the minimum distance between those 2 points. That's the kind of idea behind the solution. Okay. So these are the 2 simple problems we solved using the calculus of variation. In the next class, we will solve a very interesting problem, which is called the Brachistocone problem. And after that, we will derive the Lagrange's equations of motion from this Hamilton's principle and this calculus of variations. Okay, that's all for today. Thank you.